Hi, today we finished chapter 7 and we finished actually our course with the section 7.5, which is the spanning trees. So definition actually the name says, so let G be a graph T is a spanning tree of G if what? Number 1, T is a subgraph of G containing all the vertices. And 2, T is 3. So this is the definition, and then easy theorem that proposition 751 proposition first one says every connected graph has a spanning tree. And number 2, every 2 spanning trees of the same graph have the same number of edges. Proof, I don't know if I'm going to write a proof, just more like comments. So basically spanning tree is in a way the most efficient way to cover a graph without redundancy actually, so to keep it connected but without redundant paths between the vertices. So generally what we do is the following. This is just a common sense explanation. So let's start with let G be connected graph. And then what? If it's a tree, done. If G is not a tree, that means he has a circuit, not a tree. Means he has a circuit. What do? We cut one edge, and that will keep it connected. You remember that theorem. And then what happens? Then we revisit. So since it's still connected, we then ask, is it a tree or not? If it is, we are done. That's a spanning tree. And then, so cut an edge. Cut edge. Repeat. And then what would I do? At the end, we have to stop cutting the edges because the number of edges is finite. So when we stop, what happened? Why did we stop? Because there are no circuits anymore, and tree is still connected, so it is a tree. So it's fairly simple. Number 2, why 2 spanning trees of the same graph have the same number of edges? Since spanning trees include all the vertices, so if G has an element, then there are n-1 edges. We know that as a property of trees. Not G. If T is a spanning tree, then it also has n vertices. But now for that tree, we know it has n-1 edges. So each 2 spanning trees must have n-1 edge, so they have the same number of edges. So the question is, I think it's obvious, why is it important to find spanning trees? So we want to keep our graph connected, but in the least expensive way. And then the question is, how do we find, so what are the algorithms to find some spanning trees? And I will mention 2 algorithms We can also use the algorithm that we just explained, actually, but that one considered not to be too efficient because we don't have a plan. We just do it kind of in an arbitrary way, but we can still do it. So here it is, example 751. Here is a triangle. Here is a triangle. Here is a triangle. And here is connection. The labeling is A, B, C, D, E. There, yes, F, G, H. So there are vertices here. So this is a connected tree, and it's not. It is a connected graph, and it's not a tree because it has circuits. So what do? We cut the first. We look at the first circuit, and then we remove this, and that will not lose connectedness. So then what do? Then we say, all right. So there are more circuits. So remove an edge. So we'll remove this one. Let's say remove that circuit. It's still connected, but still there are circuits. Then what do? We remove this one, maybe this one to have less branching. So here it is. And then this is a tree, covers all the vertices, and there are no circles, so it is a tree, and everything's fine. And then now I will mention two famous algorithms using the same graph. So this would be two other algorithms for the same one. Let me use the old picture. So what was the old picture? So here's the graph, here's the graph, here's the graph, original graph. And then we want to talk about two famous graphs techniques. And the first one is depth first search. Algorithm. And then the other one is breadth first search. First search algorithm. In a depth first search algorithm, here is the procedure. We choose one vertex to be the root. What do we do then? We build the longest possible path. The longest possible path from that root. And then what? When we finish that path, when we cannot add anymore, and at the end we will stop, of course, because everything is finite, then there are two options. We either cover all the vertices, then we are done, that path is actually your tree, or there are still some vertices that are not covered. Then what happens? We backtrack down the path until first time we have someone from uncovered vertices being connected to our path, then we go in that direction and cover that vertex and so on and so on. So whenever we get stuck, we backtrack and then cover the other vertices. When we get stuck, we go backtrack and so on. So what would that be the case? So how did we do this one? We said the following. So I'll do it on top of this one. I'll go like this. I start with A, and then I cover one. It doesn't matter. So you don't choose. You don't have strategy. You name the basic one. C, and then what? Are there? Can I continue my path? Yes, I can continue it to G, and then longest possible path from that root, but avoiding circuits. If you make circuit, of course, it's not going to be the tree, I forgot to say. So G, and then I'm going to F, and here it is, I'm stuck. So here's my path, A, C, G, here it is. Then I say, did I cover everybody? And I say, no. Then what do? I backtrack. So when I backtrack, I go from my ending point, I go back, and here's my back move, and I say, can I reach someone from here? And the answer is yes. So now I have H, so I connect with H. So my tree now will include H. Then what do? I say, all right, can I continue? The answer is no. Did I cover everybody? No. Now I backtrack from H. So from H I backtrack, and I say, can I connect with anyone else who's not covered without building a circle? The answer is no. Then I go back to C, and I say, can I connect now? And the answer is yes. Now I go to D. Can I connect more? Yes, I can. Here's my E. Here's your 3. So this is the depth first search. So generally, you make like a long branches or long path. So that 3 might be very tall. So sometimes everything finishes in one tall path, you know. So, but that's the strategy. The breadth first search goes more gradually. It says the following. Let me copy the same one. We choose a vertex. So we choose a vertex. We choose a root. Then what do? Now we include all the neighbors of the root. Neighbors of the root. And keep going. So we are building more gradually, actually, according to the distance from your root. So how would that look like in this case? Let me draw this again. Looks like this. And this one is here, A, B, C, D, E, F, G, H. So what did I do here? So that was the depth first search. In breadth first search, actually what happened if you really choose, so you cannot always see all that, you don't see things visually. You kind of scan things when you write a program, but generally the way I see it now, here's what you can do. The best thing is to take C as your start. And then what do? Neighbors of C are directly who? A, B, F, G, D, and E. And that's where the breadth comes. And basically what? We covered everybody, so C immediately, A, B, F, G, nothing connecting them of course, and then we covered D and we covered E. Now what? Is there someone else who's not covered? Yes. How do we get to H? Coming from G. So here is a tree, spanning tree, and you see the difference between previous one and this one, because first one has first one has a long branch, 1, 2, 3 branch. This one has the longest branch is 2, so they are obviously non-isomorphic. All right, and then yes, there was a side comment because there is a famous example for backtracking, and that is again one chess problem. So 7, 5, 2, nothing really, not directly with graphs, but just how to backtrack some problems. So that is important strategy for computer science, so we better discuss it, even without direct reference to the graph. You want to place 4 queens on a 4x4 chessboard so that they don't attack each other. So what do? Here's how you write the program. You say, one of the queens must be in the first column. Where do I put it? I don't know, I'll start with first. So I'll try my queen here, and then what happens? Then the second one cannot be here, so it might be here. That's my first possible attempt. But if that happens, then what do? I cannot put anyone here because these 3 fields are attacked by blue one, this one by black one, so I'm stuck. Then I backtrack and I say, all right, sorry, recheck your decision, so I return that, and then I go higher. So I try it here, and then what will happen? Yes, now I can continue here with the third one, because this one is not attacked by any of the other three. That's the only available one. But then what happens? The fourth one, there's no way to put it. So what happens? I exhausted all the options on the second one. Obviously, this is not a good choice. So I backtrack actually to the choice of the first one, and then I put first one here. But then what happens? Obviously, this is forced move because these three are attacked. Then what? On the third one, I cannot hear, but I can. He put it here, the green one, and then red one. If I have red somewhere, yes. The only possible choice is here, so we do have a solution. So generally, you just try in a systematic way all the options. Whenever you get stuck, you backtrack. The similar idea with the depth first search. And then the last subtopic is minimal spanning trees. So what is the story there with minimal spanning trees? Our trees now have weights attached to the edges. So 751 minimal spanning trees. So here each edge is assigned a weight. And then we want to choose a tree, spanning tree with a minimal. So we want tree, spanning tree with minimal total weight. And that's reasonable. Why would that be interesting? That's the price and so on. So you want to build something with paying the smallest price to do the job. And we'll do two algorithms. One is cross-calls. Algorithm. In my notes there are proof that they really do the job. I'm not going to repeat the proof here, but feel free to ask me for explanations or in the discussion board. So Prim's algorithm. So what is the difference here? In a cross-call algorithm, we include all the vertices. Then keep adding edges, according edges that have a minimal weight among the remaining ones, of course, without building a circuit, without producing a circuit. Here, it's a little different strategy. You don't include all the vertices. Here, in the cross-call algorithms, the stages are not connected. The stages are not connected graphs, necessarily. And here, the stages are connected graphs. So what do? Just include two vertices with an edge, connected by an edge. That's a start. And then what? Add among the edges connecting already included vertices with non-included ones. Choose the one of minimal weight and add it to the graph. Add it to the graph because it's not 3. It might not be. No, this one is 3 all the time. This one's not 3. All right, so let's see how it works. So I here chose an example. So here is an example. Eleven, 9, 8, 6, 15, 9, 5, 7, and 5. So here's the graph. It is connected, and we want the minimal spanning tree. So what do? Are there names for the vertices here? There aren't. It's okay. Hopefully. Well, let me give them the names. A, B, D, E, F, G. It's nicer if they are labeled. So in the beginning, I put them all in. I keep erasing here. I cannot keep them all. So no, actually not erasing, just adding. So nothing's going to be erased. One more space. So here is A, here is B, here is C, here is G, here is F, here is O. Yes, here is D, and here is E. So in the beginning, 2 and then 2 down, 3 up. Good. So what do? First, I add the minimal edge. The minimal edge among these ones is 5. Which one 5 do I add? Doesn't matter. So this one is crossed, and I will involve it here. So D is there. But then, among the remaining ones, now I will add again the minimal one, and that's CG. So CG, and I cross it. So CG is here now. So you see, this is not connected at this stage. It will become. So I have 5 and 5. Oops, sorry. Then what was the next one? Next one is 6. Is it adding the edge? No, adding the circuit? No, so I will cross it so that I'm not tempted to include it again. So here it is. That's your 6. What now? Next one is 7. So I will include it because it's minimal. So 7, and I cross it here. And then, who's the next one? I have 2 8s. Which one do I add? It doesn't matter. So let me add this 8. Really irrelevant. Am I missing something smaller than 8? No, I'm not. So here's my 8. So you see there are different ways to organize your minimal spanning tree so that 8 should be crossed. Now what? Who's my next one? This 8 is my next one, but if I include it, I build a circuit, so I cross it immediately without bringing the graph. Now who's left? 2 9s. This 9 is not good because it would build a circuit, but this 9 is good, so I include this 9. Across it from the available edges. Who else? That 11 I would not add because it will make a circuit, and actually I have everybody. So here it is. Here's your minimal spanning tree using cross-call algorithm. What is the total weight? Total weight is what? 14, 22, 28, 35. Total weight is 40. Let me check with mine. I did calculation, or maybe I didn't. No, in my notes I got. 7, 7. Oops. All right. Let me just change. Actually, I forgot to copy here. In my notes, there is a 7 there, but let's say I'll put this one to be 20, so that I don't need to erase it. So this is a little different problem from the notes. Generally, when or even 9 would be fine. So as I said, it's 7 in my notes, so then it's a different solution. But here, let's say we did a different problem, so that we don't need to change it. All right. So that was Kruskal algorithm. What about Prim's algorithm? Let me restore these numbers. So this was 5. Let me copy. This was 11. AB was 11. This was 6. This was 8. I'll keep this 9 so that hopefully we get the same result. This is 8. This is 7. This is 9. This is 5. All right. How does the Prim algorithm work? We just pick up 2 edges that we like, and of course the safest thing to do, because it's just to start with the edge with minimal weight. So I'll start with ED. So here is ED. Here is E. Here is D. And here is 5. Then what do I do? Now I want someone connecting E and D with the rest of the world, because that's what it is. You connect who's in with those who are out. So the only one connecting them are this 7, this 9, this 15, and this 6. 6 is obviously the smallest one, so I'll connect here with 6 to A. And then what happens? Then I don't even need to cross the edges, because I'm not gonna be, because they will not connect. They are connecting among themselves when they are used, and I want those that connect them with the rest of the world. Now who's in there? E is there, D is there, and A is there. And then among the edges connecting them to the rest of the world, so you see this 5 is not ready yet because I'm not there, so it's connecting just things that are outside. So from E I have 7, from D I have D, this one, I'll better cross it, so it doesn't confuse me. So, so what? So the shortest one connecting them is this 7. So I'll cross it now, I will include F. So see, as we said, this one will be, or let me make it red. So this one is 7 that we just included. Now F is among the chosen ones. Then from these 4, what is the shortest one? There are 2 shortest connections. Through A, which is 8, through F, which is 8, of course we always control, so let me do G. So I'll do G here, I'll connect, and I'll get 8. And I'll cross that 8. So now what? The red ones with black ones connect, so we cannot, this one is very short, but I cannot include it. No, can I include it with C? Yes, I can actually. That's the shortest one. Now finally, yes, because this one is not included. So generally what? I'll put C here, I will include this 5. So here is C. Red as well, and I'll cross this 5. And then what happens? Everybody is in. The only one missing is B. I have B connection missing. That's 9. So what then? So among the red ones, B to connect with the remaining ones are just these 2. Of course, I'll choose the shorter one. That's 9. When you compare these 2, they are different, they are not isomorphic, but I hope I get the same weight because they cannot be both minimal and have different weights. So let's see, 11 plus 15 plus 14 is 40, so they both have total weight 40. So these are two famous algorithms for finding the minimal spanning tree. That was our course Math 226, spring 2017.